Now we'll briefly look at the system context in terms of what Praxis did for this project. So the challenge was to write a number of the key core functions of this ID station to EAL5 standard. So we have our core functions in the middle written to EAL5, but then outside that core functionality there are a number of interfaces and stubbed components which we were permitted to write at a less rigorous, in a less rigorous manner. So we have this donut of support material which was written in Ada and Spark, a mixture of Ada and Spark. And then outside of this environment are all the simulated devices. So the system interacts with a display simulator, simulators of the token readers, and a fingerprint reader simulator. So the core component of TIS was developed using C/C, and the key principles of the correctness by construction process are to avoid introducing errors, and to do this we use sound formal notations. We avoid duplicating things, because if you say something in more than one place, if you need to change that information, then there's a risk you might forget to change it in both places or in all places, and the system and its documentation can become inconsistent. And we try to keep the system and its supporting documentation as simple as possible and keep all steps simple. The other principle of correctness by construction is to remove any errors that we introduce as soon as possible. So we accept that people make mistakes and errors get into our software development process. But we want to remove any errors as soon as possible, because the sooner we remove them, the cheaper it is. So what we do is we use strong tool-supported validation. The steps between each life cycle stages are kept as small as possible, and we try and do the things which are difficult first, so we try and manage our risk. And by using this approach, we generate our evidence as we go, rather than retrospectively try and assure the system. So if we look at the development process as a whole, this was a redevelopment, so our input was the system documentation for the previous system and a very brief view of the system in operation. And I say very brief, it was about 15 minutes, not long enough to really grasp what the system was doing. From that, we developed a system requirements specification using the principles of the Praxis Reveal methodology. And we basically undertook to understand the context of the system, its interaction with its environment, and also all the stakeholders who should be interested in how we were developing the system. We also worked through a number of scenarios to try and understand exactly what the system was intended to do. And that requirement specification was reviewed by our customer, the NSA. The next stage was to address the security aspects. We'd been provided with a protection profile which indicated a number of security aspects that we needed to justify that our system was going to deal with. And in order to do this, we produced a security target. And we also identified a number of security properties that the system had to exhibit. So moving on, we developed a formal specification. This was written in Z, which is a mathematical notation. And it defined the system, the abstract behavior of the system. So we don't look inside the system, we look at how the system interacts with its environment and focus on that interaction. And at about the same time, we developed a Z specification of the security properties. So developing the formal specification and the security properties happened fairly much alongside each other, and what we did was we produced both these documents in Z, both at the same level of abstraction, which enabled us to prove that the formal specification adhered to the security properties. The next stage was the design, and this is divided into two parts. The formal design, which is a refinement of the formal specification, again written in Z, but now we look inside the system and describe how various aspects of the system are implemented. So in the formal specification, for example, we noted that we were going to log audit data. In the formal design, we actually specified in the Z notation how we were going to manage the audit log system in terms of a number of files. And then to complement the formal design, there's also an informal component, the informed design. This document provides a mapping from the formal design to the software architecture. It develops the software architecture. And it also provides additional information that complement the design. So it provides some additional constraints, and it goes into the details of some of the file structures, which the formal design was not the best methodology to use to do. And then finally, it was a Spark implementation derived from the formal design. The testing we did was all system testing, and the system test specification was derived from the formal design, and we undertook to provide system test cases which covered all the cases that were identifiable from the formal design. So where there was a choice of behavior in the formal design, we would produce test cases to cover each choice.